we have been focusing sort of on environment, global environment, from a very large scale and long-term perspective. But obviously, much of what we care about with the environment has much more to do with the local, how it affects you locally, how you might go out and influence things. Often is it one system, one ecosystem, one place, one county, one city, one town at a time. And so we're going to do some focusing on more applied, local, and even straightforward issues pertaining to water pollution. Population density, obvious. Excuse me?
The industry.
And industrial inputs. Okay, good. Those two things. You guys are right on. Until about 1850, people didn't know where diseases came from. They didn't know what caused diseases. They thought demons caused diseases, or they thought God was unhappy with them, or they thought the bad gods were overpowering the good gods, or whatever it might have been. They had no concept that diseases were caused by organisms. Now, of course, you have grown up right from the time your mother made you wash your hands and sterilize equipment and so forth. You have grown up from the concept of what we know now to be a fact, that most diseases that you get are caused by microorganisms, and they're too small for you to see. So what people and what inventions were really important in understanding what diseases were really about? Anton von Leeuwenhoek was from Holland, a Dutchman. Okay, now he was experimenting with lenses, and he put them together, and he looked into what he called infusoria. They're infused with, he would look into water, he would look into decaying stuff, and my God, he would find all these zillions of little organisms that people had no clue beforehand existed, because there's no way you can see it. No way you can think about it. No way you could understand that the bad stinks that came out of certain things were simply the byproducts of these organisms that are doing their thing. And what's their thing? Why are these organisms there?
They're getting their food from...
Right, they're getting their food. There is a resource there. The resource is whatever it is. You, me, your tuna fish sandwich that you left out on the counter behind something and didn't come back for 3 weeks, and there it is. Well, for them, it's a resource. And you go, ick, and how stinky, and how yucky. But there are people who say that the principal source of food energy for early humans was carrion. They weren't hunter-gatherers, they were carrion eaters, like buzzards. In fact, humans would watch the buzzards circling, and then they'd run as fast as they could to get there before the buzzards ate the dead zebra or whatever. Maybe that was our ancestry. Maybe that's why we have such great immune systems. The word from the health studies that you would use is to challenge. To challenge means to introduce a pathogen. What's a pathogen? A pathogen means sickness gen, making, pathogen. Pathogens are all the things that are disease organisms for us. You have a whole list of them that you learned about when you were a kid. And I guess we took a poll here, and let's try this again. How many of you know you would not be alive except for the intervention of modern medicine? So a third, maybe even half of people here. All kinds of influenza, all kinds of cholera. Cholera is a generic term for intestinal, something in your intestine. All kinds of waterborne diseases. Come on, let's come up with some more. What other diseases? Typhoid, good one. Yellow fever, yeah.
I had blood poisoning.
Blood poisoning, just what? Blood poisoning, you don't even quite know what it is, right?
Cellulitis. Cellulitis.
Cellulitis, I don't know what that is, but you had that, huh? Okay. Don't do that again.
Lyme disease.
Lyme disease. Many of these are spread by insects. Plague. Black plague. Now, we don't live in day-to-day fear of diseases, right? I mean, we worry a little bit about it. We should. But we don't live in day-to-day fear of diseases. But people used to. Okay, now who are some of the other really important people in figuring this stuff out? Pasteur. And what did Pasteur find out? What's the process that's named after Louis Pasteur? En français.
Pasteurization.
Pasteurization. What's pasteurization mean? Heat your food before you eat it. All right? That's why people go and eat raw fish at Japanese sushi bars. Some of them get real sick. So you got to make sure it's done by very reputable folks that are doing it. Raw fish is fine, unless it's been lying on the floor in the Fulton Fish Market, you know. Okay, pasture, really important. Who else? Well, for you guys, Jonas Salk, who invented a vaccine for polio. Now, what's a vaccine? How's that work? You give somebody the disease in a form that's not going to make you sick and kill you. And your body, basically what you do is you challenge your own immune system. And your immune system generates various kinds of antibodies that go and basically glom onto or eat whatever the pathogen is. Fantastic new discoveries at the micro level, at the molecular level, about how all of these things happen, mean that we understand the processes of disease and our defense from disease vastly better than we knew in the past. And Lister, what did Lister do? Wasn't he the guy who found out that, you know, doctors' offices, you know barber poles? Barbers used to be surgeons. So you do something, the horse kicks you in the leg and you got to have your leg amputated. You take it to the surgeon and the surgeon would cut it off with a saw in a completely unclean environment with all old blood hanging around. I mean, they took pride in their bloody bandages because that indicated, oh, I'm a surgeon, you know. There's all these horrible diseases around. And I think it was Lister who found out that if you took your knife and your saw and you dipped it in carbolic acid, you know, just some caustic chemical, that your death rate went from 95% to 10% from the surgery. He didn't know why, I don't think. Maybe he knew. Is that before or after Pasteur? I don't know. So, the environment in which you live is incredibly healthier for you because of modern science. The giants of whom, in my opinion, basically lived from more or less 1750 to maybe 1910 or 1920. Now, that doesn't mean that there aren't just as good and just as smart people working on it today, but the really fundamental discoveries were made in the past, and one of the most important of which was an early statistician, and he had a big outbreak of cholera. And all this guy did was plot where the people died on a map. And he found that they were all centered around one well. And he goes, it's looking at statistical patterns. And what he did was he went and he put a cover on the well and a lock on it, and bingo, the epidemic was over. The people realized that much of our diseases, of our sicknesses, was transferred through water. Now, why should it be transferred through water? Small organisms need water. They live in this water. If there is a large source of anything in the world that is a potential energy source, over time there has been a tendency for natural selection to fill this, what we call empty niche. Niche is a functional role of organisms. So if there's a lot of dead tuna fish sandwiches lying around in the world, or their equivalent, old leaves as an example, then organisms evolve because it's an energy resource, and they will be selected to use that abundant resource. If that resource happens to be us, well, just the way it is. This egg virus that's out there probably evolved either in green monkeys or in some ancestor, common ancestor, some kind of hominoid. Why? Well, it was an opportunity. Look at all this energy sitting here, all this resources for microbes, just waiting for me to kick off and jump in and have a feast. Why don't they do it? Because my immune system, because my whole living self, part of the whole concept of maintenance metabolism is fighting off all those creatures that would like to eat me. There's about 200 species living on and in me. There's a little tiny spider mite in each of my pores, apparently. All kinds of things in my gut happily there. I need them. You can't even live without them. So we have about 200 species that we live together. And many of them can live only on humans. The logic is that therefore they must have evolved subsequent to humans. And here they are, living on us and in us. And as long as they don't cause us any trouble, it's fine. But amongst the problems you are likely to face is growing resistance to antibiotics as disease organisms, crummy little disease organisms like staph in hospitals are going to, clearly they are evolving around our medicines. Okay, now we're going to talk explicitly about water pollution. That's a kind of a background about all of this. And I want to give a kind of an overview of the relation of humans to water. Okay, let's have the lights down, and you don't have to take too many notes. Okay, I'm an ecologist professionally because I grew up loving water. I grew up in eastern Massachusetts where we had, when I was a kid, lots of clean water. We don't have so much anymore. And I went to school at Colgate, and we had an outing club, and Colgate had a place up in the Adirondacks, and I discovered the Adirondacks, and I just love rivers. I think there's something really fundamental about a nice clean river. This is the Ausable River in the Adirondacks. This is the stream in North Carolina called New Hope Creek where I did my doctoral work, and I loved it. I would be out there 2 days out of 3 for 3 years doing my sampling of photosynthesis and fish migrations and so forth. It was the only clean stream within 50 miles of Chapel Hill where I was in school. That's kind of sad. Here's a local New York State stream. And we have lots of beautiful streams around here just to go and refresh our souls, to fish in if you like, to think about, to study. Here's another nice little New York State stream. And one of the best things for me all the time in my teaching is we take, in the fall, in my systems ecology course, and we go and do a whole weekend field trip in a beautiful little stream called Little Sandy Creek up an hour north of here. And for everybody, it's a wonderful experience. Now, many of us also like streams for the fish that are there. This is a brook trout, or actually a brook char. Gorgeous fish that were the native fish that were here in our streams. And they're very, very sensitive to pollutants. And around here they are increasingly replaced by brown trout, often, you know, I love brown trout too, that are an import from Germany and from Scotland. And maybe they're the trout that do better here because they've lived with humans longer and have been selected to deal with a certain amount of pollution. Because there have been people around here for 10 or maybe 15,000 years, but in Germany there have been people there for 500,000 years. One of the first ways that we began to understand the impact of low levels of pollution was the disappearance of the brook trout. So a concept you can think about is called an indicator species. Now, what's happening in general to all of our waters is called eutrophication, the process of enrichment of the food supply. Remember, the basis of the food chain are plants. Well, you would think maybe it's a good thing, and sometimes it is, to increase plant production. But when you get too many nutrients in the water, you get too much algae, and your lake or river becomes disgusting to us and deathly to many organisms. Now, the reason is this, that although these are plants, and we all know that plants produce oxygen as they photosynthesize, when they die and sink to the bottom, they use up oxygen. The dead organic material, any dead organic material, as it is decomposed, uses up oxygen as the microbes use this oxygen for their own metabolism, for their own respiration. In order to get the energy out of the microbes, out of the waste material or out of the dead plants, they have to add oxygen to the carbon and to the hydrogen of that plant in order to do their thing, to get energy for their own life processes. This is one of the cleanest lakes left in the United States. Here are some clean lakes. Flathead Lake here in Montana. We call it pristine. It's relatively unaffected by humans, although that seems to be changing. I met my wife right here, and I was married right here, so it has a lot of meaning to me. Here we are the other way, looking back the other way. In the winter, those are the Swan Mountains behind it. It's a gorgeous setting. And here it is in this great big environment, and this is all the Bob Marshall Wilderness Area, named after ESF's own Bob Marshall. And it's basically clean because it's basically in forest. So we have a lot of clean water, for example, in the Catskills. New York City has a lot of clean water because the watershed in the Catskills are in forest. Skaneateles Lake is a very clean water lake. It's a great place to do lake ecology because we've got the dirtiest lake in the eastern United States right down there, Onondaga Lake, and we have the cleanest lake over there, which is Skaneateles Lake, and we got everything in between. Clean lakes often are very, very clear because they don't have many plants in it, because there's not many nutrients, phosphorus and nitrogen, especially, for the plants to grow very much. This is all up here is Glacier National Park. So all these watersheds are protected in national parks. Now, in Flathead Lake, we see the first signs of eutrophication, the first signs of too much nutrients. And what they did was the city of Kalispell, above the lake, put in a ban on phosphorus in detergents. And it seems to have stopped the eutrophication. That's simple. So I think that's an encouraging message to you. in these days of Enron and sleaze and lying, things work. The government listens to citizen pressure. That was the message of the fellow who was talking yesterday, and you could see it statistically. This is Spring Creek, Pennsylvania, redesigned trout stream, famous trout stream. And this is above the Penn State campus. I went to Penn State for my master's degree, and this is what I worked on. And here's lovely Penn State. Pictures look a little faded here. More Penn State. Now the point is, while I was there, they were building, that doesn't go back, but anyway, all those dorms. Penn State was enormously expanding from 10,000 students to 30,000 students. And guess what everyone, and that's famous Nittany Mountain. You know, Nittany Lions football team is Nittany Mountain. You know what every one of those students did? They crapped into Spring Creek. Not purposefully, but that's where all the toilets went. Now, it went first to the sewage treatment plant. Now, here's an example of incredibly successful technology. Environmental engineers have really done a great one on this. Not as much as we need, but it works. It's called sewage treatment plants, or trickling filters. And what you do is you take that, all the turds from 30,000 people, think of what a mountain of turds is, and puts them through these tanks of crushed stone, of stones about this big, that are managed to have lots of bacteria. And these bacteria then eat the sewage and make it much less of a problem. And downstream below the sewage treatment plant, see, this is just covered with plants. So this is super eutrophication. And you'd say, well, there's all that plants, it shouldn't be a problem for the fish because all the plants produce a lot of oxygen. See, that's all plants growing on the bottom there. So the sewage has been treated, but the phosphorus is still in there. You can just see all those plants. In other words, upstream you can see the bottom, it was kind of sandy. Here it's just plants. And what it does is this. If you go out and you sample the oxygen, here's midnight, here's noon, and here's midnight again. In the stream, above the sewage treatment plant, you have what's called a normal diel, D-I-E-L, diel curve of oxygen. Goes up maybe 1 or 2 parts per million in the day, goes down. You find that curve in most of the little streams around here. You can learn a lot from that curve. Learn about that later. But where you have a lot of plants there, huge growth of plants, during the day you have superabundance of oxygen. All those plants are making lots and lots of oxygen, but at night those plants are respiring, right? Maintenance metabolism. At night they're using oxygen. So they bring the oxygen down to about 3 parts per million. Now a trout needs somewhere around 6 parts per million to live. And I looked at the impact of this on the mayflies, the insects that lived in the stream, and showed, I think, more or less conclusively that the food chain could not survive these low oxygen times, even though we had a sewage treatment plant. So the sewage treatment plant at that time was doing what's called secondary treatment. Primary treatment is you just run it through a screen, you take out the dead mice and the condoms and that kind of stuff, big chunks of stuff. Secondary treatment is what you saw there. You reduce what's called the BOD, biochemical oxygen demand, the amount of oxygen required by the material when you put it into the stream or the lake. Tertiary treatment, which they do now, is to take the phosphorus out too. And now the stream is much healthier below the sewage treatment plant. So here's a case where biologists went out and looked at what the problem was, discussed with engineers what needed to be done, Engineers discussed it. They both discussed it with the politicians. They all decided they wanted to clean up this trout stream, make it clean like it used to be. And they all worked together, and the net effect was to clean up the stream. And one of the things that they did is they started pumping the treated sewage onto the land, into a forest, and the trees would grow better. Good use of the sewage, I think. Okay, now let's take a look at a local situation here. Onondaga Lake. Here's the dome, and of course we're right next to the dome. And here's Onondaga Lake down here, and it's still getting sewage coming in. But all of this land here we're going to talk about is old waste beds, all the way up, I guess it goes all the way up here. So this is called the most polluted lake in the United States. If it's not, I don't know what's more so. Syracuse is called the Salt City. It was a very wealthy blue-collar city 100 years ago. And the reason is, we've talked before about how wealth is generated from resources. The resources that we had here were limestone. Over to Jamesville, there's an enormous, huge hole in the ground. It used to be all limestone. And it had salt. Originally it had salt springs here. And the reason it has both of those is that this area for many hundreds of millions of years was under the sea. And the limestone is the remains of little microorganisms, little microfossils from the sea. And the salt, of course, is left over from periods when the sea dried up. Now, in 1870 or so, if you wanted to make glass in the United States, you had to import soda ash from Germany. But there was this guy in Germany, I think his name was Solvay, who figured out how to make something called soda ash, which is necessary to make glass. And so it was very expensive to import from Germany. And so what some Syracuse guys figured out was, hey, we got salt, we got limestone, I got a hold of this guy's formula, and they started the Solvay process. And for 100 years, Syracuse was the basic source of soda ash, which is necessary to make glass. Now this is what Onondaga Lake used to be. It used to be an incredible resort area. People would come up from New York City, if you can imagine this, to stay on Onondaga Lake, to go swimming. In comes the Solvay process, and I mean, here's a locomotive and a train. I mean, it's a big deal. And boy, they dumped everything into the lake. And all of these are waste beds here, see? Leftover stuff. And then other industries came along, and these other industries used mercury and all kinds of bad stuff. Mercury is horrible. If you get a little mercury, will give you something called a Monomoto disease. Well, here's a history, and we don't have enough time to go through that, but even in 1901, ice fishing were banned. 1898, the fish that was the basis of the fisheries disappeared, and so forth and so on. Next, just a whole history of insults that happened to Onondaga Lake. Mercury dumping from 21 pounds a day of mercury. It just takes a gram to give you that disease. Next. Here's all the things that are there: mercury, other heavy metals like cadmium, benzene, toluenes, iodines, chlorobenzenes. Anything with chlorine is likely to be pretty nasty. PCBs, on and on and on. All that stuff is a great place for you to come and be an environmental scientist or an environmental chemist. Every kind of pollutant you want is just right down there in that lake. Next, go up in the sediments. You see a lot more mercury being deposited in 30 to 60 meters. Next. And then more recently, 0 to 30 meters. You can see how this discharge here stopped. Can you go back one? See, there's a lot of mercury at this time here. Then that factory was closed. And next, you didn't get that anymore. And you got it down here. So this idea of environmental mapping of pollutants is a really important tool you can learn here. Next. Next. And this is true for chlorobenzene, another pollutant. Next. All of them have different places in the lake. And we can even do three-dimensional modeling. Look at the plumes of pollutants below the factories. Okay, lights. So, this is kind of an overview of pollutants, of organic pollutants, meaning sewage. It's organic because it's carbon-based. And other pollutants, including heavy metals and including complex chemicals that are all around us all the time. So there's lots left for you to deal with, and we'll see you Friday.